Hello everyone, good evening. Okay, so only 11 students are there right now. Is the audio clear? Am I audible? Okay, then let's start. So, a very slight change in the plan, let me tell you. So, I told you that we would discuss these set theory questions right now, and then we would discuss the concepts of group theory tonight. So, actually, some concepts in set theory are remaining, like some important concepts like what is functions, injective function, one function, bijection function, onto function. So these concepts are remaining, and hash diagram. So these important concepts are actually remaining. So let me cover them first. So we will cover these concepts first, and then we will see the questions, the net questions of our set theory. Okay, relations, set theory. From these topics we will see the net questions. Okay, so let's start now. So today we will start with the concepts that we had left, the concepts of set theory that we had left. We will start with those concepts. So we were discussing last time, we were discussing set theory and partial order. So partial ordering. So this was we were discussing this partial ordering. Okay, partial ordering is nothing but a relation. So you have a base set. Let's assume your base set is S. On this base set you are defining a relation R. For example, we have set of natural number. On set of natural number we can define the relation less than equal to. What is this relation? This relation means A is related to B if and only if A is less than equal to B. So this is the relation, and this is our base set. So on this base set we have defined this relation. Now this relation is called partial ordering relation. This relation is called partial ordering relation. We have seen actually all these things. We have seen the examples of partial ordering and all these things we have seen. So this relation is called partial ordering relation. And this complete thing means this set, this base set along with this relation. Okay, like this set of natural number along with this less than equal to relation. So basically this base set along with this relation, this complete pair, this pair is known as POSET, partial order set. So this is the full form of POSET, partial ordered set. Okay, so this complete pair is known as partial ordered set. You already know what is partial ordering relation. A relation which is reflexive, antisymmetric and transitive. These three properties must be satisfied. Then we will say that our relation is partial order relation. Okay, so this is the complete theory that we have seen so far. So this relation R is, remember this less than equal to, this relation is known as partial ordering relation. And this complete thing, this base set with this relation, this complete thing is known as POSET. Okay, so for POSETs, for example, I can give you a POSET. For example, you can have this set 1 2 3. Let's assume this is your base set. On this base set we can define the relation less than equal to. So when we define this relation, so finally what will be the pairs in this relation? You can see 1 will be related to 2, one will be related to 1 also, 1 will be related to 2 also, 1 will be related to 3 also, because 1 is less than equal to 1, 1 is less than equal to 2, 1 is less than equal to 3. 2 will be related to 2, 2 will be related to 3, 3 will be related to 3. So these are the pairs that we will get. You can see this relation less than equal to relation on this base set. This relation is reflexive. You can see this is reflexive, this is antisymmetric, and this is transitive. You can just check all these 3 properties, you can check. So this relation is reflexive, antisymmetric, and transitive. Okay, now this relation is basically, this relation is nothing but partial order relation. Okay, this relation is partial order relation, and this complete thing means this base set with this relation, this is known as poset. This is known as poset. Now to represent a poset, we have something special. We have something called hash diagram. So this is a special thing that we have to represent poset. Remember, to represent poset, we have this special diagram. So this special diagram, hash diagram, we get from graph representation. You already know all these things, that any relation, okay, whatever relation you have, any relation can be represented with graph representation. This we have already seen. Any relation can be represented with graph representation. Now these poset, they are special relations. They have something called hash diagram. This is a special diagram representation for poset. This hash diagram we get from graph representation only. For example, for this relation we can make graph representation. How will I make? You can see the graph representation will be like this: 1, 2, 3. Now because there is 1, 1 means 1 is related to 1, so we will have a self loop. 2 is related to 2, so we will have a self loop. 3 is related to 3, so we will have a self loop. 1 is related to 2, 1 is related to 3, 2 is related to 3. So you will see that this is the graph representation. This is the graph representation for this relation, because any relation can be represented by graph representation. So this is the graph representation. But because this relation is poset, partial ordering relation, so we have something special that is known as hash diagram. Means from this graph representation we can make a hash diagram. We can make a hash diagram. How do we make hash diagram? Very easily. Just remove the trivial things. Means, for example, if I tell you that some relation is partial order relation, if I tell you that some relation is poset relation, then what will you understand from it? You will understand that it is reflexive. So basically, as soon as I tell you that your relation is a partial order relation, then automatically these reflexive pairs, these self loops, you already know that these self loops will be there. So there is no meaning, there is no there is no significance in showing them. Basically, even if we remove these, even if we do not show these self loops, you know that these are there, because these are trivial things. For example, if let's assume nowadays if you have OD, then you can show off, because not everyone has OD. Maybe you have OD, okay, someone else does not have. So with OD you can do some show off. But what show off you will do with an old generation Nokia mobile? If you have an old generation Nokia mobile, then what show off you will do? So you can see, because this is something that nowadays everyone can afford. Okay, so there is nothing to show off here. Okay, but this is a non-trivial thing. Okay, because you can see some people have it, some people cannot afford it. So that's why this is like that. These self loops, you can see these self loops are in every partial order relation. Okay, like if there is a city of partial order relations where everyone is partial order relation, okay, then wait a second. So yes, I will see all your doubts and I will clear all your doubts. So I am saying that if you have a city, in that city, let's assume everyone is partial order relation. Everyone is partial order relation. Because in this city everyone is partial order relation, so everyone has self loops. this also has self loop, this also has self loop, this also has self loop, and so on. Everyone has self loop. So there is no need to show off these self loops. So we can remove these self loops. Okay, then finally we will get this diagram. Once we remove these self loops, because we know that these are present, but we do not need to show them. We just do not need to show them, because we already know that every partial order relation has self loops. So we have removed these self loops from the diagram representation. Remember, these are there, self loops are there. One is still related to 1, 2 is still related to 2, 3 is still related to 3, but we are not showing them. Okay, we are not showing them now. So once we have basically removed self loops, now what we can do, see, our relation is antisymmetric. Every partial order relation is antisymmetric. What antisymmetric does? Antisymmetric does basically this, that if you have two different elements, then you cannot have both of them. For example, these two things you cannot have, because antisymmetric property says that between different elements there cannot be any symmetry. So you cannot have these two things together. You cannot have 1 is related to 2 is related to 1. You cannot have, because of this antisymmetric property. So because of this antisymmetric property, what happens, that if you have two different elements, then at most one of them will happen. Means if you have two different elements A, B, let's assume, then at most one of these things can happen. Means maybe A is related to B, but B cannot be related to A. So because of antisymmetric property, what happens, basically you can only go in one direction. You can only go, for example, maybe this 1 is related to 2, 2 is not related to 1. So you can go in this direction. So because of this, wait a second. So because of the, so far we have this diagram. Now from this diagram, because of antisymmetric property, what we can do, we can put this one in the lower level. As I told you in the last class also, when we were discussing this hash diagram, I told you that because of antisymmetric property, let's assume this is in our relation, A is related to B. Let's assume that A is related to B. Because of antisymmetric property, if A is related to B, then B cannot be related to A. So this pair can be represented like this. Without arrow. Basically I can remove this arrow. Why I am removing this arrow? If I remove this arrow, then how would you know whether A is related to B or B is related to A? How would you know? So we will know this by the level. For example, this A is in the lower level and this B is on the upper level, and there is A's between A and B. So we will know that there is arrow like this. Okay, so basically all arrows are going in the upper direction. This is what I am saying. I am saying that basically all arrows are going in the upper direction. This is our representation that we are using. So we can put this 1 in the lower level. Why? Because this 1 is related to 2, this 1 is related to 3. So this 1 we can put in the lower level, then we can put 2, then we can put 2. Okay, so basically we can remove this arrow, because we know that this arrow is going upper, this arrow is going upside. Okay, so this arrow is going upside. So this we already know. This convention we have taken. Basically we have just taken this convention that in our hash diagram all the arrows will be going in the upside. Okay, now so because this, now you see this 2 is also related to 3. So what we will do, because this 2 is related to 3, so how will we represent it? We will represent it like this. Okay, so this is how we will represent it. So we can represent it like this. So this is the hash diagram that we will get. So remember, this is the hash diagram that we will get. You can see, now you will see that, okay, this 1 is related to 2. So this 1 is related to 2. 2 is related to 3. 2 is related to 3. Because of this edge you can see that 2 is related to 3. Because of this edge you can see that 1 is related to 2. But now how do you represent this transitive edge? How do you represent that 1 is related to 3? How do you represent? So very easy. Like in hash diagram, we already know that every partial order relation is transitive. We already know this thing. Okay, you know, I know that partial order relation is transitive. So So from this hash diagram, this is implicit that if 1 is related to 2, 2 is related to 3, then 1 is also related to 3. From this hash diagram, it is implicit. Like from this hash diagram, we can determine that 1 is related to 3. Why? Because you can see there is a path from 1 to 3. For example, like this you can go. Basically, you just go upside, and you will reach 3. For example, from 1 you can go to 2, from 2 you can go to 3. So that's why this 1 is also related to 3. This 1 is also related to 3, but we are not showing it. Basically, we are not showing self loops, okay, because self loops are anyway present. So because they are present in every partial order relation, so we are not showing them. We are not showing transitive edges because every partial order relation is transitive, so we are not showing transitive edges. These self loops are implicit. Basically, these self loops are implicit, means these are present but we are not showing them. Similarly, these transitive edges are also implicit, means these are present but we are not showing them. So we do not show self loops, we do not show transitive edges. We only show anti-symmetric property, means we only show these anti-symmetric property. But this anti-symmetric property also we show it in this manner. For example, if A is related to B, then we will show it like this: A and then B. This is how we will show it. Okay. So this is your theory of hash diagram. So now let's see some examples we will see. So in the hash diagram, basically hash diagram is nothing but a diagram representation, graphical representation. In this representation, we do not show self loops. These are already there, okay, these are already there, but we are not showing them. Similarly, we do not show transitive edges. We only show anti-symmetric property. In this anti-symmetric property, what we do, if A is related to B, then we will show it like this: A, B. We will show it like this. Okay. So this is our hash diagram. Let's take some examples. For example, let me take one example. You can take this. Let's assume we have 1, 2, 3, 4, 5, 6. Let's assume you have this and division. So this is your poset. You can, first of all, you can see this is a poset. This is reflexive. Why? Because every element divides itself. 1 divides 1, 2 divides 2. So it is reflexive. Every one is related to itself. What is this relation? This relation basically is A is related to B if and only if A divides B. So this is the division relation. A divides B. This is the division relation. Okay. And this is our base set. So this is reflexive because every element divides itself. This is anti-symmetric also because let's assume you have two different elements, 3 and 6. Then if 3 is dividing 6, you know that 6 cannot divide 3. So if you have two different elements, then basically these both things cannot happen together. Means if you have two different elements, then between different elements there cannot be any symmetry. Okay, that is the meaning. So basically you can say like this: if A is dividing B, and let's assume that both are different, then if A is dividing B, then B cannot divide A. So this is why this is anti-symmetric also. This is transitive also. Division relation is actually transitive. Basically, if A is dividing B, okay, A is dividing B, B is dividing C, then A will divide C. Division relation is actually transitive. So all these things like division relation is transitive, all these things, these properties, like if A is dividing B, B is dividing C, then A will divide C. All these things are basic mathematics, very basic mathematics it is. So these three properties are satisfied. Because these three properties, reflexive, antisymmetric, transitive, are satisfied, so this poset is, this is poset. This is partial ordering relation, because partial ordering relation means reflexive, antisymmetric, transitive. Now how can we represent this? So by hash diagram. So in hash diagram, the same thing you will do basically. You see, this 1 is related to everyone because 1 divides everyone. 1 divides 1, 1 divides 2, and so on. 1 will divide everyone. So just put 1 in the bottom level. Okay. Now Abdul, we are not interested in finding the result, like I am not interested in finding this result that 3 is divided, I am just concerning that 3 divides 3 or not. 3 divides 3, this thing I know. You see, A divides B, let me write like this. So A divides B, you know, when do we say that A divides B? A divides B if and only if B is equal to AX for some x, for some integer x. This we already know, right? So the division property is like this: A divides B if and only if B is equal to AX for some integer x. Okay, so for example 3 divides 3. Why? Because 3 can be written like this, 3 into 1. So that's why you can say that 3 divides 3. Okay, so remember, this is a relation here. Okay, we are not interested in finding the result. Like, I do not want to find the result, like what will be the result. I do not want to find the result when 3 divides 3. Okay, 3 divides 3, then the result will be 1, but I am not interested in that one. When we study group theory, in group theory we are interested in finding the result. What will be the result? Like when 3 divides 3, then the result will be 1. So in group theory, the result is of our interest. We are interested in the result. Okay, but in relation, basically we just want to see whether this element divides this element or not. And the definition for division is this: A divides B if and only if B can be written as A into X for some integer X. For example, this we can say that this -1 divides 3 also. -1 also divides 3. Why? Because this 3 can be written as -1 multiplied by 3. So you see, there is an integer. So that's why we can say that -1 also divides 3. Abdul, is this doubt okay? Is this doubt clear? That we are only interested in finding the relation. We are not interested in finding the result. Okay, the result we are not interested. We are only interested in finding the relation. For example, okay, let me give you this one thing. See, in group theory, when we study this division in group theory, then whenever we have this kind of situation, let's assume whenever we have this kind of situation, then what we say in group theory, because in group theory we are interested in the result. What is the result of this division? So in group theory, when we have this kind of situation, 3 is divided by 0, then in this situation basically we will say that this cannot happen, because 0 cannot divide anything. You already know all these things. 0 cannot divide anything. Okay, because in group theory we are interested in the result. But in relations, remember, in relations actually 0 actually divides 3. 0 divides 3. Why? Because this 3 can be written as 0 multiplied by 3. Okay, so remember, in relations we are only interested in finding this relation. Like you can see, in relation 0 divides 3. Why? Because I do not want to find the result. What the result will be when we divide this 3 by 0, then what will be the result? I do not want to find the result. I am not interested in finding the result. I am just interested in finding whether this 3 can be written as 0 multiplied by something. Okay, sorry, I am just interested in finding whether this okay, sorry, I should say that let's take this situation, 0 divided by 0. Let's take this situation. Sorry, actually 3 actually cannot be written like this. So in relation also 0 does not divide 3. The example I want to take is 0 divides 0 or not. So this is my question. 0 divides 0. This is my question. Now, if I am interested in finding the result, what will be the result when 0 is divided by 0? What will be the result? Then remember, the result is undetermined. Result is not result is not there, because we do not, this is indeterminate form. If you remember, this is indeterminate form. So in group theory we are interested in finding the result. What will be the result? For example, when we divide 6 by 2, then in group theory we are interested in finding this result. Okay, this result we are interested in. So in group theory we can say that 0 does not divide 0. In group theory we can say that 0 does not divide 0. But in relation we are only interested in finding like this: b is divided by a if and only if b can be written as a multiplied by something, some integer. So you see, in relations 0 actually divides 0. Why? Because 0 can be written as 0 multiplied by some integer. Let's write 2 here. So 2 is integer. So you can see in relations actually 0 divides 0, because in relations we are not interested in finding the result. So this is a very basic difference. So you must be careful about this difference. Okay, you must be careful about this difference, because here we are interested in finding the result, and if we want to find the result, what will be the result when 0 is divided by 0? Then that result is indeterminate. So we do not have such a result. Okay, this result is indeterminate. But in relations we are interested in finding this relation only. So a divides b if and only if b can be written as a multiplied by some integer. So yes, 0 divides 0. Why? Because 0 can be written as 0 into 2, some integer. Okay, so that's why 0 divides 0 in our relations. So anyway, I hope that you got this concept. So this is somewhat tricky thing, but you must remember that in group theory we are actually finding the result, and in relations we are actually just finding the relation. So that is the difference. Anyway, so what was the question that we were seeing? The question that we were seeing was like this: 1 2 3 4 5 6 this, and the relation was, yes, 3 divides 0. Yes. Why? Because this 0 can be written as 3 multiplied by some integer. What is that integer? That integer is 0. So 3 divides 0. Remember, in relations we are not interested in finding the result. So in relations we are not finding the result. What will be the result? The result in group theory, when we do like this, then the result will be 0. So in group theory we are interested in finding the result. In relations we are only interested in finding whether there is some integer, such that I can write this 0 in terms of 3 multiplied by that integer. Yes, there is some integer, that integer is 0. So yes, this 3 divides 0. So anyway, this is the concept. If anyone has any doubt, then you can ask, but this is a small tricky thing that you must be careful, that in relations we are not interested in finding the result. Remember, in relations we are only interested in finding the relationship. Okay, whether this person is related to this person or not. We do not want to find the result, we don't care about the result. Okay, so anyway, so this was anyway, if you did not get it, then also nothing to worry. Okay, in NET exam they are not going to ask you these type of tricky questions. Maybe in gate exam they can ask you. Okay, but in NET exam I don't think that they will ask you this type of tricky things. Okay, so don't worry, if you did not get it, then just skip it. Okay, don't take unnecessary burden. So this is our set, and our relation is a division relation. So how will we make hash diagram? Very easily. First you will write this one on the bottom level. Why? Because 1 is dividing everyone. So 1 is dividing everyone. You can see 1 is dividing everyone. So 1 will be in the bottom level. Now in the next level, what you can do? You can put 2. In the next level you can also put 3. In the next level you can also put 5. Why I am putting like this? Because you see, 2 is not related to 3. Also 3 is not related to 2, because 2 does not divide 3. You can see, similarly 3 does not divide 2. So you can say that this 2 is not related to 3 is not related to 2. So there is no relationship between them. I told you that whenever there is a relationship like this, whenever there is relationship like this, then you will write like this, but if there is no relationship between 2 and 3, there is no relationship, 2 is not related to 3, 3 is not related to 2, so then there is no need to put them on the different levels. Okay, there is no need, like, okay, there is no need, you can just put them on the same level. Similarly, this 3 is not related to 5, 5 is not related to 3, 2 is not related to 5, 5 is not related to 2. So this is how you can put. So but remember, 1 is related to everything, you can see. Now what is the element that is remaining? The element that is remaining is 4. So you put 4 here. Why I am putting 4 here? Because 2 is related to 4, that is the reason. 2 is related to 4, that is why I am putting like this, because 2 is related to 4. So I will put like this, 4 on this is how I will put. Now the last element that is remaining is 6. So I can put it here, because 3 is related to 6 and 2 is related to 6. Remember, 4 is not related to 6. Similarly, this 6 is not related to 4. So this is the hash diagram that we will get. So this is the hash diagram that we will get. Okay, so yes, okay, let's cover more concepts in this same hash diagram. Let's cover some more concepts we will cover. So our hash diagram, if you see, our hash diagram is like this. In this hash diagram we will cover some more concepts. So this is our hash diagram, you can see, this is the hash diagram. Now in hash diagram we have some elements, some definitions are there. The first definition is, what is minimal element? Minimal element. What is minimal element? As from the name itself you can see, minimal element means some element below whom there is no one. For example, this one is minimal because no one is below this one. You can see no one is there below this one, no one is there below this one. Okay, this 5 is not minimal. So like for our example, 1 is minimal because no one is below 1. 5 is not minimal because below 5 we have 1. 3 is not minimal because below 3 we have 1. So you can see the only minimal element we have is 1. What is the definition of minimal element? Minimal element, for example, A is minimal. If no element B is related to A. If no element B is related to A, remember, if no element B such that B is related to A, there is no such element B. So that's why you can say that this is minimal element. This one is minimal element. This 6 is not minimal because you can see this 3 is related to 6. So this 6 is not minimal. The only minimal element we have is 1. Next thing that we have is maximal element. What is maximal element? The same thing, maximal. The name itself will suggest what is maximal. Maximal means above you there is no one. See, minimal is saying that below you there is no one. Okay, below you, like you are the last ranker in your class. Let's assume in your class you are the last ranker. Maybe a class is 30 students are there and your rank is 30. Okay, your rank is 30. So you can see below you there is no one. So you are minimal. Okay, but remember, it could also happen. Let's assume that on 29th rank, let's assume the 2 students are there, student A, student B. These are on the 29th rank. Okay, 29th rank, 2 students are there, A and B. So these are minimal. Why? Because below them no one is there. Below A there is no one, below B there is no one, because they are on the same level. So below them there is no one. So this is also minimal, this is also minimal. So minimal means below you there is no one. Okay, so below you there is no one. So that is the definition of minimal. Means no element B such that B is related to A. This is the definition of minimal. What is the definition of maximal? Maximal says that above you there is no one. Above you there is no one. There is no one. What I can say? I can say like this. A is maximal, A is maximal, A is maximal if no element, no element B such that A is related to B. This is the definition. Basically, no element B is there such that B is above A. B is above A. There is no such element. So then we will say that it is maximal. In our hash diagram, what is the maximal element? In our hash diagram, maximal element is 4, maximal element is 6, maximal element is 5. Because there is no one above 4, there is no one above 6, there is no one above 5. So these are the maximal elements. So minimal element, maximal element, these concepts are okay. Then now we can see the next concept that we can see is, wait a second, is least element. Okay, wait a second. So now we can see something called third concept, that is least element. Least element. Least element means least element is unique. Basically, if least element is there, then that is unique. Like you are unique person who is or at the bottom level. You are the unique person who is at the bottom level. So for example, in our diagram, this is our diagram, 2, 3, okay, 5, and then we have 4, and then we have 6. This is our diagram. So what is least element? Least element means basically you are uniquely in the below level. For example, let's assume in the class of 30 students, you are the 30th student. Basically you are alone at the last rank. You are alone at the last rank. So you see, you are alone in the last rank, so you are least element. But let's assume on the 29th rank, let's assume 2 students are there. You are there and your friend is there. In this situation, at least you will get some feeling like, okay, I am not the only one who is at the bottom level, my friend is also there. So basically you will feel slightly happy. So this situation is different. Yeah, like in this situation, basically you are not least. You cannot say that you are least element, okay, because you are not least. Okay, this B is also basically this B is also giving you company in the last rank. So in this situation we will say that these are minimal elements because there is no one below them, but these are not least element. Least element means unique element in the last rank, unique element in the last rank. So I can say like this: A is least if for everyone, means everyone is above A. I can say that everyone is above A. For everyone is above A, means for every B, you can say that B is above A. So then we will say that this A is least. Like here, this one is least. In our example, this one is least element because everyone is above 1. The fourth definition that we have is greatest element. What is the greatest element? What is the greatest element? Greatest element is element, basically the topper, like unique topper, like the first ranker, and no one is there on the. For example, let's assume there is only one element in the first rank, then he is the greatest, like greatest element. Okay. Now assume the situation. Let's assume two students are there who got the first rank. Let's assume 2 students got the first rank. Now this student cannot say that I am the greatest because this student also got the first rank. So basically these students are not greatest, but they are maximal because no one is above them. So they are maximal, but they are not greatest. Greatest means unique. Unique means A is greatest if for everyone is below you. Basically everyone is below you. For every B is below you. Okay, so this is the definition. Basically for every element, every element is below you, so then you are greatest. Okay, every element is below A, then A is greatest. In our example, there is no greatest element. Why? Because you can see we have 3 maximal elements. These are 3 maximal elements, so no one is greatest because everyone, each of them is first ranker. You can say each of them is first ranker, each of them is topper. So there is no greatest element. Or you can say like this. the greatest element definition says that everyone is below you, but 6 is not below 4, 4 is not below 6. So that's why no greatest element is there. So this is the definition of greatest element, this is the definition of least element. Let's take next poset we will see, and let's try to find out greatest element, least element, everyone. Greatest element, least element will be unique if they are present. If they are present, then they will be unique. They may not be present, okay, they may not be present, but if they are present, then they will be unique. Let's take next example. So the next example we can take like this. Let's assume this is your set 1 2 3 4 5 6. This is your set and the relation is less than equal to. So this is your base set and this is your relation less than equal to. This is your relation less than equal to. Now for this set, find minimal set of remember minimal element is like minimal element may not be unique. There can be more than one minimal element. There can be more than one minimal element. Okay, so minimal element is not may not be unique. So you need to find the minimal set, means minimal element set. Okay, minimal set. You need to find the maximal set. You need to find the least element. If it is present, then you need to find it. If it is not present, then you need to say that there is no least element. Also you need to find the greatest element. If it is present, then you need to find it. If it is not present, then you need to say that does not exist. So these 4 things you need to find. Try this question. So first of all, we will create hash diagram for this question. See, in the same question I am doing multiple things. I am showing you how to construct hash diagram. I am also showing you how to find these things. So first we will try to construct hash diagram. You see 1 will be in the bottom. Why? Because 1 is less than equal to everything. You can see 1 will be in the bottom. Okay, 1 will be in the bottom. Why? Because 1 is less than equal to everything. 1 is less than equal to 5, 1 is less than equal to everything. So 1 will be in the bottom because 1 is related to everything. Okay, so 1 will be in the bottom. Now 2 will be here because 1 is related to 2. You see where 3 will go. Where should I put 3? 3 I cannot put here. 3 I cannot put here. Why? Because 2 is related to 3. So 2 is related to 3. Because 2 is related to 3. So I need to put like this. So I need to put like this. Okay. Now where can I put 4? You cannot put 4 here. Why? Because 3 is related to 4. Because 3 is related to 4, so we need to put like this. So we need to put like this. Now where should I put 5? I should put 5 here. Why? Because 4 is related to 5. 4 is related to 5. So I need to put like this. 4, 5. I need to put like this. Now where should I put 6? I should put 6 here. So you can see there is a chain here. You can see there is a chain here. This is a chain. Actually, if you remember, we have already covered this concept. Chain is also called total ordered set. This concept we have already covered. Chain is total ordered set. This concept we have already covered. So you can refer to the our previous lecture on POSET, previous lecture on set theory. There we have already covered that chain is nothing but total ordered set. So this is chain. You can see there is a chain here. Okay. Now in this chain you can find the minimal set. There is only one minimal element, remember, that is only 1, because this 1 is minimal. There is no one below 1, you can see. There is no one below 1. So this 1 is minimal. This 6 is maximal because there is no one above 6. Okay, so that's why 6 is maximal. Least element is again 1. Least element is 1 and greatest element is 6. So least element is 1, greatest element is 6. One thing you can notice, if you notice one thing, here I written set 1. If you see here I written like this. This minimal set I wrote like this, and this least element I wrote like this. Least element I did not write like this. Why? Because least element will be unique if it is present. if least element is present, then it will be unique. It will be unique. That's why I am directly putting 1. Greatest element will be unique if it is present. That's why I am directly putting 6. But here you see, in our minimal element set, I am putting like this, because minimal element may not be unique. So it will be a set. It will be a set. Similarly, this maximal element, this also will be a set. This also will be a set. Least element will not be a set. This will be a unique element if it is present. Similarly, greatest element will be a unique element if it is present. So this is the difference you can see. Okay. So anyway, so this is our hash diagram for this relation. Now we can see the next concept, something called upper bound. Upper bound. What is the upper bound? What is the upper bound and what is the lower bound? Okay. So for example, let's take one hash diagram. We will take this hash diagram. Let's consider this hash diagram. Now for this hash diagram, my question is, what is the upper bound? Upper bound, basic actually this upper bound of set B comma C. This is my question. Upper bound of set B comma C. Okay, upper bound of set B comma C. This is my question. So let's see the concept of upper bound. What is the concept of upper bound? So in upper bound concept, what we have some set. For this set we need to find the upper bound. For this set we need to find the upper bound. So upper bound basically will be set of those elements to which this B is also related, C is also related. So you see, basically upper bound means upper bound, you go upper. Okay, so you need to go up on the upper side. So in the upper side you see there is D, there is E. So what is the upper bound? D is not upper bound. Why? No, D is not upper bound because B is not related to D. You can see from this hash diagram, you can see that B is not related to D. B is related to E, C is related to D, C is also related to E. I told you, because of transitivity, you see, because of transitivity, you see, we have this arrow, we have this arrow. So we can say that C is related to E also. So we can say C is related to E. But remember, B is not related to D because we can go like this, but we cannot come below. We cannot come like below. Okay, once we have gone upper side, then we cannot come in the lower side basically. Okay, we cannot go below. So this is why B is not related to D. So upper bound will not be D, upper bound will be this. This will be upper bound. What is the definition of upper bound? This is the definition. Let's assume you have a set. Let's assume you have a set. In this set, let's assume you have some people. Now upper bound means some godfather to which this is also related, this is also related, this is also related, this is also related. Okay, this is the upper bound. For example, if you have seen the Welcome movie, then in the Welcome movie, if you want to find the upper bound of Majnu and Uday, if you want to find the upper bound, then that upper bound will be, first of all, the one upper bound is RDX, because Majnu is related to RDX and like Uday is related to RDX. And there is another upper bound in the Welcome 2 movie. There is another upper bound, that is, I think, what is that, Don Nasiruddin Shah, what is the character name? I am forgetting the character name, but anyway, that is the upper bound. You can see Nasiruddin Shah, you can write Nasiruddin. So in the Welcome 1 movie, this RDX was the upper bound of Majnu Uday, and this Nasiruddin Shah is the upper bound of Majnu Uday in the Welcome 2. So these are the upper bounds. What is the definition of upper bound? The definition is very simple. If you are finding upper bound of some set, then upper bound will be those elements to which everyone is related. Like this, to which everyone is related. So Okay, anyway, this is the upper bound definition. Okay, and this is the analogy of Welcome movie. Anyway, if you have seen this movie, then you might find this analogy nice. If you have not seen this movie, then you should watch this movie. Anyway, so this is our upper bound. So now we can find the something. For example, I can ask you question. Let me ask you second question. What is the upper bound of this set? What is the upper bound of this set? Tell me. Manisha, in the hash diagram we have already mentioned that all the arrows are going upside. In the definition of hash diagram, we have taken this assumption. Okay. The definition of hash diagram says that all the arrows are going upside. That assumption we have already taken. I told you that whenever we have this type of situation, A is related to B. Whenever we have this type of situation, then we represent this like this. We will represent it like this in hash diagram. In hash diagram, we will represent like this. So all the arrows are going upside. This we have already seen in the hash diagram. Okay. So in the hash diagram, all the arrows are going upside. Okay. So now you can find the upper bound of A. I am asking the upper bound of A. Let me draw it again. And my question is what is upper bound of this set? Many students are actually answering wrong. Yes, we can take analogy for cricket also. Okay, we can take it next time. Anyway, so let's see upper bound of A. I told you actually many students are still doing wrong. Okay, I told you the upper bound of any element is set of those elements to which it is related. Like everyone in this set, we only have one element. In this set, we only have one element. Like in the Majnu Uday example, if you remember Majnu Uday, there we have two elements in our set. We need to find the upper bound of this Majnu Uday. Then upper bound will be element to which both of them are related. So like this RDX is upper bound. Why? Because to RDX, Majnu is related, Uday is related. Similarly, Nasiruddin size upper bound. Why? Because Majnu is related, Uday is related. So this is the definition of upper bound. You need to find upper bound of this set. This is one set. This is one element only. So the upper bound will be those elements to which it is related. So the upper bound of this will be the upper bound of this will be, first of all, the upper bound of this will be A also. Some students are not taking A. The upper bound of this A will be A also, because A is also related to A. Don't forget that. A is also related to A. Okay, A is also related to A. So A is also in the upper bound, B is also in the upper bound, C is also in the upper bound, D is also in the upper bound, E is also in the upper bound. You see, A is related to everyone. A is related to A is related to B, A is related to C, A is related to D, A is related to E. So this will be the upper bound. Okay. Next question, you can try this. Let's try this. What is the upper bound of this? What is the upper bound UB of this? Tell me the UB of this. Now this is like two elements are there. Like Majnu Uday, you can think whatever. Two elements are there. So what will be the upper bound of A comma B? The upper bound of A comma B, you can try. The upper bound, see, the upper bound will not be A, because B is not related to A. So upper bound will not be A. Okay, like Majnu is not godfather of Uday, Uday is not godfather of Majnu. Both are basically on the same level. Both are friends. They are not godfather of each other. So similarly, A will not be upper bound because this B is not related to A. B will be upper bound B will be upper bound because A is related to B is related to B. So B will be upper bound. C will not be upper bound. C will not be upper bound because B is not related to C. You can see this B is not related to C. D will not be upper bound. D will not be upper bound because B is not related to D. E will be upper bound because A is related to E, B is related to E. So our upper bound will be basically, our upper bound will be B comma E. This will be our upper bound. So hopefully everyone got this concept. Now let's see the concept of lower bound. What is the lower bound concept? The same, just reverse this concept. If you want to find the lower bound of some element, let's assume you have two elements. If you want to find the lower bound will be those elements which are related to both of them. Which are related to both of them. Which are related to both of them. Then this will be the lower bound. So this is how we will find lower bound. Okay. So for example, you can just reverse this direction. For example, if I want to find the lower bound of RDX, let's assume I want to find the lower bound of RDX, then the lower bound will be Majnu, the lower bound will be Uday, because you can see this Majnu is related to RDX, this Uday is related to RDX. So this is how you can say that the lower bound of this is Majnu Uday. Similarly, for example, you can find this situation. Let's assume you have RDX and you have this Nasiruddin Saab. What is the name of, in Welcome to, what is the name of his character? I am forgetting the name. Anyway, so the what will be the lower bound? Lower bound still will be, for example, Majnu will be lower bound. Why? Because Majnu is related to both of them. So Majnu will be lower bound because Majnu is related to both of them. Uday will be lower bound because Uday is related to both of them. Okay. For example, Akshay Kumar will not be lower bound because Akshay Kumar is related to RDX. In Welcome first movie, Akshay Kumar is there. He is related to RDX, but he is not related to Nasiruddin Saab because in Welcome 2 movie, Akshay Kumar is not there. So Akshay Kumar, and the name of Akshay Kumar character is Rajiv. So you can see this Rajiv is related to RDX, but Rajiv is not related to Nasiruddin Saab. So that's why this Rajiv is not in the lower bound. So anyway, this is the concept. Basically, whenever you have some set, let's assume you have some set A, B, C, D. You have some set. Then the lower bound will be element which is related to everyone. If you have some element, let's assume this element is there. This element is related to A, B, C, but this element is not related to D. Then this will not be lower bound. So let's see our next question. The same question we can take A, B, C, D, E. So now in this question, you find the lower bound of A comma B. Find the lower bound of A comma B. What will be the lower bound of A comma B? So let me tell you, let's see everything one by one. Which of them is lower bound? Which of them is lower bound? Let's see. A is lower bound because A is related to both of them. A is related to A is related to B. So A is lower bound. B is not lower bound because B is not related to A. B is related to B, but B is not related to A. So B is not lower bound. C is not lower bound because C is not related to B. D is not lower bound because D is not related to B. E is not lower bound because E is not related to B. Remember, E is not related to B. B is related to E. E is not related to B. Okay, so remember this thing. Because in hash diagram, all the arrows go. In Welcome 1, Feroz Khan was RDX. In Welcome 2, the character of Nasiruddin, there is Nasiruddin Saab, his character name. Okay, Feroz Khan was RDX in Welcome 1. Anyway, let's not go in too much movie. So anyway, this is so lower bound of this set will be only this. Remember, this will be lower bound. If you are writing this, then this is not correct answer. The correct answer will be set. This will be correct answer. Remember, this thing is not same as this thing. So you need to take care of these small things. Okay, this thing is not same as this thing. So your answer will be like this. Actually, your answer should be like this. Okay, this is more correct. If in exam, let's assume 4 options are there. One option is this, another option is this. Then you should answer this option. You should not answer this option, because lower bound will be a set. Okay. Now tell me, what will be the lower bound of D? Lower bound of D. Tell me. The lower bound of D you can just find very easily, because there is only one element. So just find those elements which are related to D. For example, D is related to D. Okay, yes, wanted bhai, yes. Satish is also fan of Welcome movie anyway. So wanted bhai, yes, RDX was wanted bhai. Okay, so you can see the lower bound of D will have D, because remember, D is related to D, so D will also be there. Don't forget this D. This D will also be there. Why are you forgetting this D? Okay, don't ignore him, because D is also related to D. Now B will be there because B is related to D. A will be there because A is related to D. C will not be there, E will not be there. So the answer will be ABD. Okay, ABD. So the cricket reference has come, ABD. So the answer will be basically this, ABD Villiers. Okay. So don't forget D. Some students are forgetting D. Why are you forgetting D? D is also related to D. In the upper bound also we have seen this, such similar example we have seen in the upper bound also. So don't forget this D. Okay, so if all these concepts are clear, then now we will see. So we have seen something called lower bound. Now let's see what is the greatest lower bound. So greatest lower bound is a lower, this is unique. If it is existing, then it will be unique, because this is saying that, let's assume you have lower bound. Let's assume, for example, you have this set A, B, C. Let's assume you have this set, and the lower bound of this set is 1, 2, 3. Let's assume this is a lower bound. So let's assume this is lower bound. So this is lower bound. Now in this lower bound, what is the greatest element? In this lower bound, what is the greatest element? Basically, greatest lower bound means in this lower bound, what is the greatest element? Okay, you already know the concept of greatest element. You already know the concept of lower bound. Just mix them. What is the greatest element in this lower bound? Similarly, least upper bound. Similarly, we have least upper bound. Means in your upper bound, what is the least element? So these are the two concepts we have. Let's see example. Let's assume you have this question A, B, C, D. Let's assume you have this concept. This is your hash diagram. Let's assume this is your hash diagram. Okay, so for this hash diagram, you need to answer first question. What is the upper bound? So remember, I am just asking upper bound. Upper bound of A, B. What is the upper bound of A, B? Okay, let's see this. Let's assume this is your hash diagram. Tell me what is the upper bound of A, B. So the upper bound of A, B will be, this is E. So the upper bound of A, B will be, upper bound of A, B will be very easy, D, E. This will be upper bound. DE, this will be upper bound, because you see upper bound means godfather. Okay, so this A comma B have this godfather D, A comma B have this godfather E. So this upper bound is D comma E. Now if I ask you what is the least upper bound, what is the least upper bound? This is known as LUB, least upper bound, least upper bound. So first of all, remember this concept. Least upper bound means in the upper bound what is the least element? In the upper bound what is the least element? Okay, in this upper bound what is the least element? You see, in this upper bound no one is least element, because you can see this D is not related to E is not related to D. So in this upper bound, there is no least element. So in this upper bound I can say that least upper bound does not exist, or you can say that least upper bound is empty set. No. Why? Because least upper bound will be a unique element if it is existing. So I can say that least upper bound does not exist. Okay. So this is how you can find. Let me take this example would be nice. Actually, this is nice example. See this example: B, C, D, E. See this example F. Let's write it F here. Okay, wait a second. Let me draw it again. A, B, C, D, E, F. Okay, tell me the upper bound of, first of all you need to tell me the upper bound of DE. What will be the upper bound of D comma E? Upper bound of D comma E. Okay, let me quickly tell you. The upper bound of D comma E will be D comma B. So you need to find the upper bound. Upper bound means element to which both D comma E are related. So B will be in the upper bound. This B will be in the upper bound. Why? Because both D comma E are related to B. C will be in the upper bound because both D comma E are related to C. A will be in the upper bound because both D comma E are related to A. So this will be your upper bound. Now tell me what is the least upper bound of D comma E. Tell me what is the least upper bound of D comma E. Least upper bound. Least upper bound. So you can try. Let me answer. Least upper bound means in the upper bound you find the least element. While you are not finding least element. See, you need to find least element in the upper bound. Least upper bound means least element in the upper bound. So in the upper bound is like this. The upper bound is this. The upper bound is A, B, C. This is upper bound. In this upper bound you need to find least element. So there is no least element. Why? Because see, B is not least element because B is not related to C. C is not related to B. So you can see there is no least element here. There is no least upper bound. Next, let's take the next question. Okay, let's take this question. What is the lower bound? What is the lower bound of B comma E? What is the lower bound of B comma E? Tell me. So okay, Pile, you see this is our upper bound. Upper bound is A, B, C. These three elements are upper bound. A, B, C. These three elements are our upper bound. In these three elements, just focus on these three elements. In these three elements, you need to find the least element. You already know what is least element. Least element means element which is least. Least means basically element which is below everyone. Basically, just focus on A, B, C. Now in these A, B, C, there is no least element. Why? Because you see, this B comma C both are not related. So it's like this, the A is topper and in the second rank we have B comma C. This is the second rank. So there is no least element. There is no least element because the second rank has B comma C. These are the second ranker and A is the first ranker. So there is no least element. Least element means unique element which is least. So in here, in this example, you can see there is no least element of BCA. Did you get it? Well, let me know if you got it. Let's see the lower bound of B comma E. The lower bound of B comma E will be, so E will be there, lower bound E will be there because E is related to both B comma E. So E will be there. Okay. Now F will be there. So this will be the lower bound E comma F. This will be the lower bound E comma F. Remember, D will not be in the lower bound. D will not be in the lower bound because D is not related to E. So the answer will be E comma F. Now tell me the greatest lower bound of B comma E. The greatest lower bound of B comma E. Greatest lower bound. So let me tell you this concept. See, you have found lower bound. First of all, you have found lower bound. After finding lower bound, now you try to find, in this lower bound you try to find the greatest element. This is your lower bound. So this is your lower bound. These two elements are sorry, this is your lower bound E comma F. This is your lower bound. Okay, so this is your lower bound E comma F. This E comma F. This is your lower bound. In the lower bound you try to find the greatest element. So just try to find the greatest element in E comma F. What is the greatest element in E comma F? That is E. So E is the greatest element. So this will be the greatest element. See, this will be the greatest element. So E will be the greatest element. No, F will not be the greatest. Greatest you need to find. In this lower bound you need to find the greatest element. Lower bound is E comma F. In this E comma F you need to find the greatest element. So the greatest element will be E, because greatest element means the topper. The topper is E and the second ranker is F. So the topper is E. So the greatest element will be E. So the answer will be E. Remember, answer will be E. Answer will not be like this, because greatest lower bound will be unique. If it is existing, then it will be unique. So don't write like this. Don't write like this, because greatest lower bound will be unique if it is existing. Similarly, least upper bound will be unique if it is existing. Just like greatest element, least element, those are unique if they are existing. They may not exist, but if they are existing, then they will be unique. Okay, now someone is asking, sir, B comma F nahi aa sakta lower bound. The lower bound, see, the lower bound of B comma E we are finding. See, we are finding lower bound of B comma E. In the lower bound, B cannot come. Why? Because B is not related to E. No, Sarah, we will not take B in the lower bound because B is not related to E. See, are you getting my point? So lower bound, in the lower bound we will not, for example, okay, let me write it again. So we have this type of diagram: A, B, C, D, E, F. This type of diagram we have. Okay, so in this diagram we were finding the lower bound of B comma E. In the lower bound, B cannot come. Why? Because lower bound definition says that lower bound will be element which is related to both of them. Okay, which is related to both of them. But you see, this B is not related to E. This B is not related to E. So B will not be present in the lower bound. Is this point clear? Sarah, Surinder, let me know if this point is clear. Direction is always upside. The concept of hash diagram we have told that in the concept of hash diagram all the directions are actually, we are not showing the direction, but all the directions are upside. in the hash diagram we are not showing the directions, but all the directions are upside. Okay, so anyway, all these concepts you have seen, we have seen all the concepts, greatest all these concepts, so you can practice on your own. Okay, we will also see the previous year net questions. At that time also we will see these concepts again, we will see the let me ask you, actually there are too many messages, so let me request you, if your doubt has not been cleared yet from the beginning of the lecture till now, if your doubt is not clear, then you can ask right now. So Nivedita is asking GLB not getting. Okay, let's see GLB. So let's assume you have this diagram. Let's assume you, so this is your diagram, A, B. This was the diagram that we took, D, E, F. This was your diagram. So this was your diagram. In this diagram I was asking, let's assume I am asking greatest lower bound, remember greatest lower bound of, let's assume B comma E. What is the greatest lower bound of B comma E? So first you find the lower bound of B comma E. First you find the lower bound of B comma E. So what will be the lower bound of B comma E? The lower bound of B comma E will be E comma F. Is it clear? The lower bound of B comma E will be E comma F, because E is related to both BE, F is related to both BE. So this will be the lower bound. So our lower bound is this. Remember, our lower bound is this. Now you need to find the greatest lower bound, means you need to find the greatest lower bound. Okay, so you need to find the greatest lower bound. This is your lower bound. This is your lower bound. This is your lower bound. In this lower bound you need to find the greatest element. So you have two elements. So basically in the class you have A, in the class you have F, and you need to find the greatest. So the greatest will be E, because you can see F is related to E. F is related to E. So E is the first ranker, F is the second ranker. So E is the greatest. E is the greatest. Remember, in this lower bound you need to find the greatest element. Greatest lower bound means greatest of lower bound. So this is your lower bound. In this lower bound you need to find the greatest element, and that greatest element will be E. This will be your greatest element. Is it clear now? Padam, Nivedita, is it clear now? Okay, if anyone has any other doubt that I have not solved yet, then you can ask again. Just copy paste it again, and so that I can see. Okay, all these concepts are over. So actually let me go through the slides. So these slides, so basically the hash diagram looks like this. In the hash diagram, remember one thing, in the hash diagram we are not showing arrows, but all the arrows are upside. All the arrows are upside. All the arrows are upside. Okay, all the arrows are upside. Okay, but we are not showing them. Okay, we are not showing them. For example, we are not showing these arrows. Similarly, we are not showing these self loops. Self loops are also there. So we are not showing self loops, but self loops are also there. Similarly, we are not showing transitive edges. We are not showing transitive edges. For example, you see this dorm is related to Italian, because dorm is related to American, American is related to Italian, so dorm is also related to Italian. So this transitive edge we are not showing. In hash diagram we do not show self loops. In hash diagram we do not show transitive edges. Okay, in hash diagram we do not show we do not show arrows. But remember, all these things are implied. All these things are there. All these things are there, but these are implied. Okay. For example, self loop is there, but we are not showing it. Like we have, for example, I have laptop, but there is no show off. Everyone has laptop nowadays. Okay, like most of the people are having laptop nowadays. So I have laptop, but I am not showing it. I am not doing the show off. Okay, so it's like that. So we are not showing self loops, we are not showing transitive edges, we are not showing arrows. But remember, all these things are implied, means all these things are present, but we are not showing them. Self loops are present, but we are not showing them. Transitive edges are present, but we are not showing them. arrows are present but we are not showing them. Arrows are always upside, all arrows are always going upside. So this is the hash diagram. We have seen the definition of hash diagram, we have seen how to construct hash diagram. Okay, so this is the hash diagram, for example. Now we can see, for example, this is also hash diagram. This is the hash diagram in which this is the hash diagram. For example, in this hash diagram, basically our base set is set of whole numbers. This is our base set, and the relation is less than equal to. So set of whole numbers 0, 1, 2, 3, 4, set of whole numbers, this is our base set, and less than equal to, this is our relation. So if you draw the hash diagram, then what will be the hash diagram? Hash diagram will be like this: 0 is related to 1, 1 is related to 2, 2 is related to 3, 3 is related to 4, because all the arrows are going upside. Remember, 0 is also related to 2. This is transitive edge, this is transitive edge, this is transitive edge, but we are not showing these transitive edges. All these transitive edges we are not showing. Also 4 is related to 4, 3 is related to 3, 2 is related to 2. All these things we are not showing, but they are present. They are there, but we are not showing them. Okay. So anyway, this is the hash diagram for this relation. Wait a second. For this relation, this is the hash diagram. In this hash diagram, you can find the, for example, in this hash diagram, you can find the minimal set. You can find the minimal set, and the minimal set will be this. Basically, this will be the minimal set, because there is no one below 0. What will be the maximal set? There is no maximal. Basically, a maximal set is empty, because there is no maximal element, because it will just go on. After 4 there will be 5, 6, 7 and so on. So there is no maximal set, there is no maximal element. You can see there is no maximal element, so maximal set will be 5. What is the least element? Least element is 0. Least element is 0, because everyone is related to 0. What is the greatest element? Greatest element also does not exist, because there is no greatest element, because you will just keep on going. After 4 there will be 5, 6, 7 and so on. So there is no greatest element. Okay. Now for example, in this question I can ask, what is the lower bound of 4, 1? What is the lower bound of 4, 1? Lower bound of 4, 1. Yes, diagram actually cute होते हैं. In the Welcome movie you can see there is a diagram. Majnu bhai makes the painting where there is a horse, and on that horse there is a donkey. So that diagram is cute, you can see. So anyway, diagrams are also cute sometimes. Anyway, so what is the lower bound of 4, 1? The lower bound of 4, 1 will be 1, 0. This will be the lower bound. Remember, the lower bound of 4, 1 will be 1, 0. This will be the lower bound. Now if I ask you, what is the greatest lower bound? What is the greatest lower bound? So in the lower bound you find the greatest element. This is your lower bound. This is your lower bound. You find the greatest element. The greatest element will be 1. So the greatest element will be 1. So this will be the your greatest lower bound. Okay. So this is how you can very easily find. For example, if I ask you, what is the upper bound of 1, 10, 100? What is the upper bound of 1, 10, 100? What is the upper bound? You can very easily find upper bound will be 100, 101, 102, 103 and so on. So this will be your upper bound. Remember, this will be your upper bound. Okay. If I ask you, what is the least upper bound? Least upper bound of 1, 10, 100. What is the least upper bound? So this is your upper bound. This is your upper bound. In this upper bound, you need to find the least element. In this upper bound, you need to find the least element. So the least element will be 100. So this will be your least element. Okay. So anyway, this is the complete concept you have seen. If anyone has any doubt that I have not covered yet, then you can ask again. Please ask again, because there are too many messages and I cannot see all the messages right now. So if you have any pending doubt, you can ask again. Okay, kindly ask again if you have any pending doubt. So anyway, this is the summary. We have seen partial order. Partial order relation is reflexive, antisymmetric, transitive. So this is the summary. Okay, partial order relation means reflexive, antisymmetric, transitive. Hash diagram. Remember, hash diagram is for partial order relation. This hash diagram, this is a special diagram that we have for partial order relation. Okay, so for partial order relation we have this special diagram, hash diagram. Then we have something called total order. You already know what is total order. In the last class we have already discussed it. Total order means first of all it must be a partial order. After this is partial order, then every two elements must be comparable. Every two element, you take any two element, they must be comparable. Like for example, you take any two elements a comma b, then they must be comparable. Comparable means a must be related to b, so they must be, basically every two elements must be comparable. And this total ordered set we have already seen in the last lecture, you can refer there. This is also called chain. Why it is called chain? Because when you make the hash diagram of this total order set, when you make the hash diagram, that hash diagram will look like a chain. You can see this hash diagram will look like a chain. Okay, so you can take one example. For example, let me give you one more example. Okay, try this example. Set of integers and less than equal to. Set of integers and relation is less than equal to. So this relation you can try. This relation is actually total order. Why? Because if you see the hash diagram of this relation, that will be like this: 0, 1, 2, 3, 4, and so on, and -1, -2, and so on. So basically you can see there is a chain here. Okay, so this is your chain. This is a total order set. Okay, are elements not set of element? Yes, GLB. These wherever you find greatest least. Okay, wherever you find greatest least, then those are unique elements. Those are not set. Those are unique element. Okay. So is this doubt clear, Manisha? Those are unique element if they are existing. Then those are unique elements. For example, you take this set. For this set, if I ask you, my question is, what is the least element? Tell me, what is the least element in this set? In this poset you can find the least element, and the least element is actually, there is no least element. In this set you can find there is no least element. Because there is no least element, you will just keep on going down. Okay, -3, after -3 you will be -4, after -4 -5 will be there, after -5 -6 will be there. There is no least element. Least element does not exist. For example, if I ask you what is the greatest element does not exist, because you will just keep on going upward. After 4 there will be 5, after 5 there will be 6, and so on. So you will just keep on going forward, upward. So there is no least element, there is no greatest element. Okay, so this is how you can find all these things. Total order basically is a chain, because when you make the hash diagram of total order, then you will get a chain. You will get basically a single chain, a straight line you will get. A straight line means a chain you will get. Okay, you will not get like this. No, you will get a straight line. Straight line means chain you will get. Okay, now we have seen all the concepts actually, but this comparable concept we have not seen so far. This comparables concept, this is very easy concept. We say that two elements are comparable. We say that A and B are comparable. A and B are comparable if and only if A is related to B. So this is the definition of comparable. Comparable means basically they are related. You know one thing you already know, that in the poset, because of antisymmetry, if A is related to B, then B cannot be related to A. if A is related to B, then B cannot be related to A because of antisymmetry. Let's assume A and B are different elements. Let's assume that A and B are different elements. Then if A is related to B, then B cannot be related to A because of antisymmetry property. So A and B are comparable if and only if A is related to B. For example, you see this diagram: A, B, C, D, and there is E. Let's see this diagram. Okay, in this diagram, okay, let me actually draw it again so that you do not get confused. So this is A, B, C, then you have D, and then you have E. So this is your diagram. In this diagram, if I ask you question, is B, C comparable? Is B, C comparable? Is B, C comparable? So you can just see they are not comparable. Why? Because B is not related to C. C is not related to B. You can see B is not related to C. C is not related to B. So they are not comparable. Comparable means basically two elements are comparable if they are related to each other. Like for example, if I ask you the question, is C, E comparable? C, E comparable. Tell me, C, E comparable. C, E are comparable, yes. Okay, C, E are comparable. Don't forget transitive edges are there, but we are not showing them. Don't forget it that you see C is comparable to E. Actually, C is related to E. Okay, because of transitivity. Because you see, all arrows are going upward. Remember this thing, all arrows are going upward. So C is related to D, D is related to E. So by transitivity, C is related to E. So remember, C is related to E. So C and E are comparable. Okay. So actually, Neetu, we should not say that they are related to each other. We should, because you see, because of antisymmetric property, when we say that two elements are related to each other, see, when we say that two elements are related to each other, then it means that A is related to B, B is related to A. This is the meaning of related to each other. But in poset, because of antisymmetry property, if you have two different elements A, B, then you cannot have both of them. If this is there, then this cannot be there. So we can say that A is related to B. We cannot say that B is related to A. So we will say that A is related to B, B is not related to A. This is how we will say. So actually, this is called comparability. Comparability means two elements are comparable if and only if A is related to B. This is how we say comparability. Okay, in the poset, basically I can say in the poset, because in poset we have antisymmetry property. In the poset, two elements are comparable if and only if A is related to B. So this is your definition of comparability. Is it clear, Neetu? Yes, if A is related to B, then B is not related to A. If these are two different elements, remember these must be two different elements, because if let's assume A is 3 and B is 3, then 3 is related to 3, then 3 is related to 3. Basically, in this case A is related to B, in this case B is also related to A. So remember, they must be different elements. Okay, antisymmetry property says that between different elements there should be no symmetry. If it is there, then it should be not there. Basically between different elements means A should not be equal to B. Between different elements there should be no symmetry. Okay, so this is the antisymmetry property. Anyway, okay, so someone was asking antisymmetric and asymmetric. Antisymmetric and asymmetric. Let me quickly cover this. Asymmetric, antisymmetric. In antisymmetric, we are saying that between different elements there should be no symmetry. In antisymmetry, basically what we are saying that if two different elements are there, then there should be no symmetry. Okay, between different elements. Remember, in this basically we are saying that between different elements there should be no symmetry. There should be no symmetry. What it means? It means like this: if A is not equal to B, then you cannot have both of them. You cannot have both of them. Either this will be there or this will be there or none of them. Basically both of them cannot present simultaneously. They cannot be present simultaneously because between different elements there should be no symmetry. This is the antisymmetric. Asymmetric says that there should be no symmetry. Different, same, I do not care. Basically this asymmetric is very like a very straightforward person. He is saying that I don't care whether you are same or whether you are different. There should be no symmetry. Basically this asymmetric even does not allow this kind of pair. This kind of pair are not allowed by asymmetric. Antisymmetric allows this kind of pair. You can see antisymmetric allows this kind of pair, A comma A, because A is related to A is related to A. So between same elements there can be symmetry in antisymmetric. So this kind of pair are allowed. These kind of pair are allowed. But this kind of pair are not allowed in asymmetric. This is the only difference. Basically in asymmetric there should be strictly no symmetry. Strictly no symmetry. Strictly no symmetry. So for example, if I give you this, consider this example. Let's assume that this is your relation 1, 1, 1, 2. This relation is antisymmetric. This relation is antisymmetric. Why? Because between different elements there is no symmetry. This relation is not asymmetric because of this 1, 1. This antisymmetric allows reflexive pairs. Basically this ATS antisymmetric does not have any problem with reflexive pair. There is no problem with reflexive pair. Asymmetric does not allow reflexive pair. So for example, this relation is not asymmetric. This relation is antisymmetric. For example, consider this relation. This relation is antisymmetric. This relation is asymmetric. This relation is antisymmetric. This relation is asymmetric also, because you can see this relation is asymmetric. This relation is antisymmetric. So this is the definition of asymmetric and antisymmetric. Is it clear? Who was asking? Let me see. So someone was asking this. Is it clear? Pratibha was asking. Pratibha, is it clear? So this is our comparability basically. For example, in this example, we have seen this example. We have seen this kind of example 1, 2, 1. This was our example. We have seen this type of example. If you remember, we have seen this type of poset. In this poset, you can see that 2 and 3 are incomparable. 2, 3, they are not comparable. Or I can say that incomparable, because 2 is not related to 3 is not related to 2. Okay, so you can see 2, 3 are not comparable. 2, 4 are comparable. 1, 6 are comparable, because 1, 6 are comparable. 1 is related to 6. 3, 5 are not comparable, because 3 is not related to 5. 5 is not related to 3. So you can see this is the comparability thing. Next, we have seen this total order. We have already seen hash diagram. We have already seen. In hash diagram, we remove self loops, we remove transitive loops, and basically we remove the edges, the arrows we remove. But remember, all the arrows are there, so these arrows we remove, but remember, all the arrows are there and in the upward direction. All the arrows are in the upward direction. So this is your hash diagram. In this hash diagram you can see this A4, A5, this is your maximal set. This is your maximal set, this A4, A5, because there is no one above them. This A1 is your minimal set. Okay, this A1 is your least element. There is no greatest element. So this is how you can find all these things. Okay, so you can try all these questions. I will share these slides. Okay, I have not shared them yet, but I will share them today. I will share all these slides today. So next concept that we have is functions. What is a function? Let's quickly cover this function. What is a function? This function is also a special type of relation. Remember, this is also a special type of relation. This is so special. This is actually the most special. I can say that this is most special. Okay, this is even more special than equivalence relation. This is even more special than partial poset. So we have seen many special relations so far. Okay, so far we have seen many special relations. Okay, Khushbu, we will cover lattice. In the NET exam, do we have lattice? Someone told me that in NET exam lattice is not there. Just let me know, in the NET exam do we have lattice? Just let me know, I will cover it. If it is there, then I will cover it. Is it there in the NET exam or not? Is there any question from lattice in the NET exam? Specifically in the NET exam. In GATE exam we have, but in the NET exam do we have it? Okay. So okay, first we will cover this function. First focus on this function. We will come back to lattice later. So first focus on this function. What is function? Function is a special type of relation. This is so special. This is the most special actually. Okay, this function is so special that it does not even take the name relation. For example, we have seen equivalence relation. So this equivalence relation is also taking the surname relation. This partial order relation is also taking the surname relation. This reflexive relation is also taking the surname relation. But this function is so much special that it does not even take the surname. So you can see this is so much special. What is a function? Relation you know from set A to set B, relation. From set A to set B, relation. What is relation? Relation is nothing but, for example, A, B, C, D. Okay, 1, 2, 3, 4. Relation is basically you can do anything. This is your relation. For example, this is your relation. But this is not a function. Okay, this is not function. Okay, don't worry. We will check whether lattice is in the syllabus or not. We will check. If it is in the syllabus, then we will cover. So don't worry. Okay, no, nothing to worry. We will cover it. Okay. And Pratibha is asking relations on matrix. Relation on matrix, that might be question. If you have any question like this in the previous NET exam, if you have any question that you have doubt, then you can ask. Because there is no like this is not a separate concept. They might have asked some question. Relations on matrix. Okay. So anyway, you see, okay, just focus on functions. Okay, right now just keep your focus on functions. You see, relation is anything from set A to set B. Whatever you do, that is relation. For example, whatever you do, for example, you can do like this, that is also relation. Whatever you do, that is relation. But this is not a function. Function is a special type of relation. Function is a special type of relation in which every element of this set, every element, remember, every element of this set is related to exactly one element of this set. Means exactly one element. Remember, exactly one element. So you cannot have this. Because this element A should be related to exactly one element. Okay, exactly one element. So remember, every element should be related to exactly one element. Every element should be related. For example, this B is related to 3, C is related to 3, so A is related to 1. So exactly 1. You can see every element is related to exactly one element. Remember, this B and C are related to 3. That is allowed. That is allowed. Why? Because B is related to exactly one element, that is 3. C is related to exactly one element, that is 3. A is related to exactly one element, that is 1. So this is the definition of function. So such type of relations are called function. So whenever we have a function from set A to set B, let's assume this is your set A, this is your set B, then function from set A to set B is nothing but a relation such that every element of this set should be related to exactly one element. For example, this is also a function. Remember, this is also a function because every element is related to exactly one element. So for example, this is also a function. Okay, for example, this is also a function, this is also a function. Okay, this is also a function. Okay, so this is also a function. For example, A, B, C, 1, 2, this is not a function. Why this is not a function? Two things are violated. Two things. First thing, that this element is related to more than one element. I told you every element must be related to exactly one element. So this is the first violation. The second violation is that every element should be related to exactly one element. This B is not related to anyone. C is not related to anyone. I am saying that every element should be related to exactly one element. So this is function, this is not function. So remember this thing. It's like this. The functions are basically like this. It's like child father relation. It's like child mother or child father, whatever. It's like that. For example, every child must have exactly one father anyway. So but remember, two different child can have same father, or they can have different father also, but basically for everyone there must be. So this is like this. Anyway, this is analogy if you want to okay, so this is the analogy. So basically every element should be related to exactly one element, that is our function. Now in our function we have this. Let's assume we have a function from set A to set B. Let's assume we have a function f. Now this set A is called domain. This set A is called domain. So this is called domain. Remember, this is called domain. And this set B is called codomain. This set B is called codomain. So for example, this is a function. You can see this is a function. For example, this is a function. This is also a function, right? Why? Because every element in the domain, this is the domain. This is domain. This is codomain. So every element in the domain should be related. Every element should be related to exactly one element in the codomain. So A is related to 1, B is related to 2, and so on. Now this is your function. This is your function. Now in this function, this is called this set B is called codomain. This set A is called domain, and this is called image of. So if I ask you what is the image of A, the image of A is 1. So I can say that image of small a is 1, image of small b is 2, image of small c is 4. So basically these are called images. Like you can put some mirror here, then you can say that image of A is 1, image of B is 2, image of C is 4. So this is the terminology. Okay, image of. So I can write like this: f of A means this A is related to 1 under f. This is the meaning. F of A means 1, means this A is related to 1 under f. Under this function, this A is related to 1. So I will write like this: f A is equal to 1, f B is equal to 2, f C is equal to 4. Or you can say f A equal to 1 means image of A is 1, f B equal to 2 means image of B is 2, f C equal to 4 means image of C is equal to 4. So remember, this is the concept of image and all these things. Let's see few more example. few more terminology A, B, C, 1, 2, 3, 4. Now let's take this function. Let's take this function. In this function, the image of, so I can say that image of A is 1. Okay, image of B is also 1. Image of C is 4. So this is the image. I can say pre-image. I can say pre-image of 1. Basically, it's like this. The image of A is 1. Then the pre-image of 1. What is pre-image of 1? The pre-image of 1 is A comma B. This is the pre-image of 1. Are you getting? Pre-image of 1 is A comma B. I can say that pre-image of 2 is 5. That is empty set. Empty set means 5 because there is no pre-image of 2. Similarly, pre-image of 3 is empty set 5 because 3 has no pre-image. Similarly, pre-image of 4 is C. This is pre-image of 4. Okay, pre-image of 4 is C. So this is the concept of pre-image. Okay, so this is the concept of image. This is the concept of pre-image. Let's take one more definition. So we know that this is domain and this is codomain. Okay, now consider this function. Consider this function. In this function, if you see in the codomain, just focus on codomain. In the codomain, if you see this 1, 2 have pre-image, this 1 has pre-image, this 2 has pre-image, 3 has no pre-image, 4 has no pre-image. Nidhi, every element should relate to exactly one element. See, B is related to exactly one element, that is 2. C is related to exactly one element, that is 2. Okay, like it should not happen. For example, this should not happen. Okay, this type of situation should not happen. But this type of situation can happen. Okay, are you getting? So, for example, this type of situation also can happen. Okay, in the functions. So this type of situation can happen because in this situation, this element is related to exactly one element. This element is related to exactly one element. Similarly, but in this situation, this element is related to more than one element. So this type of situation should not happen. This type of situation is allowed. For example, this is a function. Okay. Now, in this function, if you see this 1 and 2, they have pre-image. This 1 has pre-image, this 2 has pre-image. Okay. But the 3, 4 are not having pre-image. 3 has no pre-image. 4 has no pre-image. So if you see this set 1, 2, this set 1, 2 is called range. This 1, 2, it is called range. What is the definition of range? Range is subset of codomain such that those elements basically those elements which have pre-image. So 1 has pre-image, 2 has pre-image. So this is the range. So this is the definition of range. This is we have seen all the concepts, all the basic concepts. So for example, this is a function because you see this apple is related to exactly one element, this is related to exactly one element, and this is related to exactly one element. Okay, now for we can see remaining concepts. For example, we have seen this function is also called mapping. This function is also called mapping. This is also called mapping. Function is also called mapping. Both are same thing. Mapping or function, both are same thing. And so we have seen all these things. Okay, range, we have seen domain, codomain, everything we have seen. Okay, let's see the next concept. So now we will see some special type of functions. Special functions. So just focus here. Special functions. We have some special functions. For example, if you see this function a, b, c, 1, 2, 3, 4, if you see this function, then this function is special. Similarly, if you see this function a, b, c, 1, 2, 3, this function is also special. For example, you see AB1, this function is also special. For example, you see ABC 1 2 3 4, this function is also special. So we have this special function. Now let's see this type of function is called one function, and there is another name, that is injective. One function or injective function, this is the name of this function, injective. What is the meaning of this one function? Basically, in one function what happens, that different elements of domain are related to different elements in the codomain. You see, in one function basically you cannot have this type of situation. In one function you cannot have this type of situation. In one means different elements will relate to different elements. This is one means different elements will relate to different elements. Okay, for example, here different elements A and B are different element, they are related to different element. B and C are different element, they are related to different element. A and C are different element, they are related to different element. So this is called one or injective. How can you remember it? You can remember like this. Injective means injection. You know, one injection can be given to one person. So one syringe, if you have a syringe, let's assume you have a syringe, okay, one syringe you have, then that syringe can be given to one person. Same syringe cannot be given to different person. So you can think of this set as a set of injections. You can think of set of syringes or set of injections, whatever, syringe or set of injections. So basically, do not give same injection to more than one people. So for example, this type of situation you should not have. The same injection you cannot give to more than one people. So you should not have this type of situation. So this is analogy. Remember, this is just an analogy, but the definition basically says that different elements should relate to different elements. So this is a special type of function. This is one injective function. Okay, you can remember it by the example of injection if you want to remember, by the example of syringe. So this is a special function, one function. Let's see this function. This function is also one. This function is also one. Okay, why? Because different elements are related to different elements. Okay, you can see different elements are related to different elements. For example, this A is related to 1, B is related to 2, 3 is related to C is related to 3. So this is again a one function. This is again a one function. Let's see what is this function. This function is another special function. You can see this is not one. First of all, this is not one because A and B are related to same element. Different element are related to same element. Basically, you are giving this same injection to more than two people, and you know what happens when you do this. There is a specific disease that will happen. So anyway, you can see this is not one. This is not injective. The another name of one is injective. Both are same basically. This is just another name. So this is not one. But this function has one property. What is that property? In this function, every element of codomain has pre-image. You see, in this function, every element of codomain has pre-image. Every element of codomain has pre-image. So this is onto. This is called onto. And the another name for onto is surjective. Surjective or surjection. So this is, remember, this is a surjection. Surjection means surjective, because every element of codomain has pre-image. For example, this is not surjective. If you see this is not onto, because 4 has no pre-image. This 4 has no pre-image. So this is not onto. This is not onto. The another name of onto is surjective or surjection. So this is not onto. This is onto. You can see this is onto. Why? Every element in the codomain has pre-image. So this is onto. So this is onto. This is onto. This is not onto. This is not onto because 4 has no pre-image. 2 has no pre-image. So this is not onto. This is not one also. This is not one. Why? Because different elements are having same image. So basically this same injection, this injection 1, this is given to two different people. A and B. So this is not 1 1, this is not on 2. This is on 2 but not 1 1. This is both 1 1 and on 2. This is 1 1 but not on 2. So we have seen everything. Now this function which is both 1 1 and on 2, you see this is 1 1 and on 2, 1 1 and on 2. This type of functions are called bijection, bijective, bijection. Bijection means 1 1 and on 2, means injective and surjective, injective and surjective. Okay, so this is our some special functions we have seen. Okay, let me cover what is this bijection. Let me cover it. Bijection means a function. For example, consider this function a b c 1 2 3. Now consider this function. This function you can see, this is bijective function. This is bijective function, or you can say bijection, bijective function. Why? Because this is both 1 1, this is both 1 1. Basically this is 1 1 means injective, 1 1 means injective. So this is both 1 1 and this is on 2 also. This is on 2 also. On 2 means surjective. On 2 means surjective. So this is on 2 also, this is surjective also. Okay, so this is bijection, bijection or bijective. So this is bijective function. Remember bijective. Bijective means 1 1 and on 2. 1 1 and on 2. Okay, so 1 1 and on 2, or you can say injective and surjective. Anyway, so this is your functions, special functions we have seen. There is another name for bijection. There is another name for bijection. The another name for bijection is 1-to-1 correspondence. Correspondence. Don't confuse. 1-1 function is different. 1-1 function is different. 1-1 function is different. 1-1 correspondence is different. 1-1 correspondence. 1-1 correspondence. Bijection is also called 1-1 correspondence. Why do we call it 1-1 correspondence? Because bijection functions is like this. Bijection function is like this. Because everyone has like a partner. For example, if this is set of male, this is set of female, then for example maybe this is husband of A1, this is husband of B2, this is husband of 3. So basically this is like, so this is why this is called 1-1 correspondence. Or you can say maybe for example if these are centers. For example, if this is election center 1, election center 2, election center 3, then this A is the superintendent of election center 1, this B is the invigilator of election center 2, and this C is the invigilator of 3. So this is how you can see. Basically 1-to-1 correspondence. Basically everyone has been given some responsibility. So this is why we call bijection as 1-to-1 correspondence. Okay, so remember this. And also few things you can note, that if you have, let's assume you have a function A, let's assume you have a function B. Suppose that this has more cardinality than this. For example, this has cardinality m, this has cardinality n, and let's assume m is greater than n. Let's assume m is greater, means this has more number of elements. Let's assume this has more number of elements and this has less number of elements. Basically this cardinality is greater than this cardinality. In this situation you cannot have 1-1 function. In this situation you cannot have 1-1 function. Let's try to make 1-1 function. Let's try to make 1-1 function. So because I want to make 1-1 function, so I am giving this injection A I am giving to 1, this injection B I am giving to 2. Now this injection C I have to give to 2 people, because this is the only injection that is remaining. So I have to do like this. I have to do like this. So you see, you remember, note this thing, very special note. If you have this domain has more cardinality than the codomain. If this m is greater than n, if this m is greater than n, then you cannot have 1-1 function. 1-1 function is not possible. Okay, so this is why it is not possible. Okay, because this basically it's like this. Let's assume there are 10 people and there are 5 injections. Then of course you will have to give same injection to more than 1 people. Okay, you will have to do it. Okay, so it's like this. Okay, basically if this has more elements, this has less number of elements, if m is greater than n, then one function is not possible. Now let's see the next situation. Let's assume that this has less cardinality and this has more cardinality. For example, this has 3 and this has 4. Means n is greater than n. Let's assume n is greater than m. So for example, this has less cardinality, this has more cardinality. Means this has cardinality 3, this is cardinality 4. In this situation, onto function is not possible. Onto function is not possible. Why? See, let's try to make onto function. Let's try. So what you will do, for example, because we want to cover all the elements of codomain. Onto function says that every element of codomain must have a pre-image. Basically, every element of codomain must be covered. This is the onto function. Onto function means every element of codomain must be covered. Okay. So let's try to cover every element. Let's try to cover every element. So let's cover this 2. Let's cover this 3. Now you cannot cover 4. You cannot cover 4 because remember, you cannot do like this, because if you do like this, then the definition of function is violated. Definition of function is violated. So you cannot do like this. So we can say that this 4 cannot be covered. This 4 cannot be covered. Okay. So I can say that onto function is not possible whenever you have this type of situation. Whenever you have this type of situation, then onto function is not possible. Okay. So we have seen two things. If this domain has less cardinality than codomain, then onto function is not possible. If this domain has more cardinality than this codomain, then one function is not possible. So you know what is bijection. Bijection means both 1 and onto. Both 1 and onto. This is bijection. Bijection means both 1 and onto. So what should happen in bijection? In bijection, m should be equal to n. Basically, this should be equal to this. M should be equal to this. Then you will have bijection. Then you will have bijection. Why? Because if m is not equal to n, if m is not equal to n, then either m will be greater than n or m will be less than n. If m is greater than n, then 1 not possible. If m is less than n, then onto is not possible. We want both of them. We want 1, we want onto. We want both of them. Both of them we want. Then if we want both of them, then m should be equal to n. So remember, bijective function, I can say that f a to b. I can say that if you have function from a to b, then bijection, or you can say bijective function, or you can say 1 correspondence, or you can say 1 correspondence. So we will say that if you have a function from a to b, then bijection or bijective function or 1 correspondence is possible, or you can say exist, if and only if cardinality of a is equal to cardinality of b. Okay, if and only if cardinality of a equal to cardinality of b. Means if you have same cardinality a, b, c, 1, 2, 3, then you can easily make bijective. So if you have same cardinality, then bijection function will exist. At least one bijection function will exist. Okay, at least one bijection function will exist if you have same cardinality. So this is like this. This is like this. If a cardinality is equal to b cardinality, then bijective function will exist. Means at least one bijective function will be there. Similarly, if bijective function is existing, then a cardinality will be equal to b cardinality. This is the result. Okay. So we have seen everything about functions. We have seen what is 1 function. 1 function is also called injective function. You can remember, if you want to remember this thing, then you can remember by the example of injection. Basically, do not give same injection to more than 1 people. So this codomain, you can think of it as a set of injections, set of syringes. Okay, you can think like this. Okay, this is just an analogy. Okay, you can make your own analogy. You don't need to if you are not fan of welcome movie, then you can make your own analogy. Like you can make a Harry Potter analogy. For example, this Harry Potter, Hermione, and this what was that third person? Okay, what was that third element? So anyway, Hermione and the third element is there. Ron Weasley. Okay, so you can see they have the godfather. What is the godfather? That is Dumbledore. So this Dumbledore is the upper bound of Harry Potter. Similarly, Dumbledore is you can say upper bound. Similarly, this Professor McGonagall. Okay, so she is also upper bound. Okay, you can see. For example, so this is how you can. Okay, you can make your own analogy. For example. Anyway, okay, this is enough. So this is injective function. Next you can have, this is surjective function. So we have seen surjective function. We have seen injection and surjection, means bijection. We have seen bijection. Okay, bijection is also called one-to-one correspondence. Okay, all these things we have seen. Maximal element, minimal element, greatest element, upper bound, lower bound, greatest upper bound, greatest upper bound, least lower bound. All these things we have seen. This lattice we will cover it if it is in the net syllabus. Today I will ask you can let me know on the WhatsApp, in the discussion group. You can let me know if from lattice in NET exam, if they have asked any question. If it is currently in the syllabus, then we will cover it. Don't worry, we are not going to leave out anything. Okay, so you just let me know. If it is in the syllabus, then we will take one more class, and someday I will cover it. Okay, it won't take a lot of time, just half an hour it will take, and we will cover it. Okay, so this maximal element, minimal element, greatest element, all these things we have already seen. Minimal element, least element, all these things we have seen. Okay, upper bound, lower bound we have seen. Let me just see if, okay, lower bound we have seen. For example, if you have this poset, in this poset the minimal set, if you find the minimal set, then that will be A comma B. This will be the minimal set. If you find the maximal set, then that will be C comma D. This will be the maximal set. Okay, if you find the greatest element, there is no greatest element. If you find the least element, there is no least element. Okay, for example, if you find the upper bound of A comma B, then that will be D. This is the upper bound of A comma B. If you find the lower bound of C comma D, if you find the lower bound of C comma D, then that will be A. So all these concepts we have seen. Okay, so okay, for example, you can I will share all these slides with you. Don't worry, we will see all these slides. Okay, for example, this is your poset, this is your hash diagram. In this hash diagram you can do all kind of experiment. For example, you can find maximal you can see what is the maximal element here. The maximal element set here is GHI. This is the maximal element set. So anyway, you can do all these kind of things. Okay, you can see, you can just refer these are the answers. Okay, so this is, so a lot of practice material I have put in these slides. You can refer to these slides. All the concepts we have seen. Okay, all the concepts we have seen. DNE means do not exist. Do not exist. This is the meaning of DNE. Do not exist. Okay. So then we have lattice. Actually, I have put lattice in these slides, but then someone told me that lattice is not in the syllabus. So if it is in the syllabus, then we will cover it. Okay, don't worry. So anyway, this is enough. So we have covered everything. Okay, so okay, the one last announcement actually. So the last announcement is that actually today I have to go. I have to go for actually I have to go to Delhi tonight. So tonight is my bus is there tonight. So I'm not able to take this next lecture actually. So wait a second. Let me on. So what I'm saying. So far the things that are remaining. Let me tell you the things that are remaining. So combinatorics is remaining. This combinatorics is remaining. Combinatorics means counting, basically counting. This counting is remaining. Combinatorics, counting, all these things are remaining. Okay, so this is the one topic that is remaining, combinatorics and counting. Okay, so this is remaining. Okay, and the next thing that is remaining is the previous NET question solution. Okay, for example, graph theory. Okay, graph theory previous NET question solutions are remaining. Graph theory solutions are remaining. These graph theory lectures I have already shared the link. You can 3 lectures I have shared the link on our Acadflix channel, on our Acadflix YouTube channel. 3 lectures I have already taught this graph theory actually. These 3 lectures I have already taught, so you can refer to those lectures for graph theory. Because if I again cover these things, then 3 classes will be wasted, and we are having crash course. So because we are having crash course and we have time limits, so that's why you can refer to these graph theory lectures on Acadflix YouTube channel. There you can find graph theory lecture 1, graph theory lecture 2, graph theory lecture 3. So this solution session is remaining. Previous year NET question solution is remaining. So in graph theory, in group theory also some topics are remaining. In group theory some topics are remaining. All these ring, field, all these things are homomorphism, isomorphism, these things are remaining. And solutions of set theory, all these. So these 4 or 5 things are remaining. Okay, so we will take all these classes. Okay, I will take all these classes, don't worry. Somehow I will try to manage all these classes. So today I can't take the next class. I have to prepare for my journey. And don't worry, I will not leave out anything. Okay, so all these things that Abdul is sharing, all these things we will see. This counting, mathematical induction, all these things we will see in the combinatorics. Basics of counting, this we will see in the combinatorics. Pigeonhole principle we will study in the combinatorics. Permutation, combination, inclusion, exclusion principle, mathematical induction, these things we will study in the combinatorics. Don't worry. This probability we will not study in discrete mathematics. This probability is a part of engineering mathematics. So this probability we will not study right now. Okay. Okay. So I will be back on 10th October. I will be back. So after 10th October we will take these classes. You can practice. Okay. Till then you can practice. Other subjects will start now. All the other subjects like algorithm, all these other subjects will start now. Kapil sir will take classes from now onwards. Okay, so you can practice these discrete mathematics questions. You can solve all the NET questions. You can practice more questions. If you want more questions, then you can solve gate questions also if you want. But actually gate question, the level of gate is more than the level of NET. So I would suggest that you solve NET questions. Maybe you can solve NILIT questions, because NILIT has the same level of NET exam. So you practice, you solve all the questions, and whenever I will be back on 10th or 11th of October, I will be back. After that, we will try to somehow manage these classes. We need around 3 or 4 classes we need. In the crash course schedule, actually we do not have these many classes, but I am not teaching. You can see this crash course I am teaching like a complete course. You can see this crash course does not feel like a crash course. Almost it feels like a complete course. Okay, you might be getting the feeling of complete course. So in the complete course we will see all these things in more detailed manners. So far you can see this discrete mathematics we have seen for around 15 or 20 hours. This discrete mathematics we will see by the end of this discrete mathematics, by the end of all the chapters, by the end of all the topics, this discrete mathematics will be of around 15 to 20 hours. But in complete course, this discrete mathematics will be for 50 hours. So you can see a lot of practice will be there, a lot of practice, a lot of concepts, every single thing will be covered. I told you earlier also, I told you that if this is the NET syllabus, then in the complete course we will cover this much syllabus, so that you can also crack GATE exam. So this discrete mathematics we will study in complete course in such a way that you will be able to get full marks in the NET exam, also in the GATE exam. So this is how we will cover it. So this discrete mathematics we will cover for around 15 hours. Okay, 50 hours. So in complete course. So in this NET exam plus GATE exam, everything you will be, you can say everything you will be able to solve. Full marks you will get in discrete mathematics. We will do this much practice. Okay. So the timing of complete course will be shared by Abdul sir in the discussion group, in the WhatsApp discussion group. You can ask. Okay, and as I told you, if you want to enroll for complete course, then you can enroll, because in complete course all these subjects that we are studying right now, all these subjects we will study in much more detailed manner. Discrete mathematics, TOC, DBMS, and compiler design. These are the 4 subjects that I will cover. Some subjects Abdul sir will cover, some subjects Kapil sir will cover, some subjects Priyanka ma'am and Pawan sir, so they will cover. So anyway, all these subjects will be covered in very detailed manner. Okay, I can say that these subjects of mine, the subjects that I can say that all these subjects that I will cover, all these subjects I will cover from the GATE point of view, so that you can solve all the questions of NET, and also you can solve all the questions of GATE. So this is how we will cover it. Okay, because once you are able to solve GATE questions, then automatically NET questions will be solved. You can think like this. This NET is a subset of GATE. If you are able to solve GATE questions, then automatically NET question will be automatically over. So these 4 subjects, I can promise that these 4 subjects we will study from the GATE point of view, so that you can get full marks in NET exam also, in GATE exam also. Okay everyone, thank you. See you after few days, after 1 week I will see you. And sorry for this this class that we have tonight. I can't take this class. Okay, but I will cover it, so don't worry, I will cover it. I can't take it tonight. Okay, and if you have any doubt, then you can ask your doubts on the WhatsApp. You can ask your doubts individually also. You can ask on the group. If no one is answering on the group, then you can personally message me. I will answer it. Okay, and if you are interested in the complete course, if you are interested in taking the admission for complete course, then you can ask in the WhatsApp group. You can tag Abdul sir, and you can ask all the details about the complete course. Okay. Yes, yeah, in complete course we will solve GATE questions also. GATE questions, NET questions, everything we will cover. Okay, we will cover from the point of view of GATE, so that you can solve NET questions, you can solve GATE questions. Basically you can solve any exam. Once you study for GATE exam, once you study the concepts from the GATE exam point of view, then you can solve any exam, you can crack any exam, whether that is NEET exam, NET exam, ISRO exam, BARC exam, GATE exam, TIFR, any exam you can crack. Okay, okay everyone, thank you.